Hey guys, welcome to the first lesson on limits. I'm going to make this video a nice, short, and easy video explaining limits, which are essential in calculus. I hope you subscribe to my channel, take a look at my playlist, and my hope is to make calculus so easy and fun for you. At any point during the video, stop the video and try the problems for yourself. So good luck. In mathematics, a limit is the value that a function approaches as the input, x, approaches some value. Okay, so let's take a look at what I mean by this. First of all, in this problem here, I just drew a graph. I don't even know what the graph is, but I do know that it's a polynomial, and I do know that it is continuous. One thing that we notice in the function is that there's no vertical asymptote, there's no holds, there's no jump. It just goes. I'm going to try my best to trace over this in a highlighter. It just goes without ever picking up our pen. It's continuous, okay? So this is actually important because if we notice this in any of our graphs, then we know the limit will always exist at any x values. Okay, so first I'm going to show you how to denote it. I'm going to call this guy f of x. I don't know what this guy is, and I actually don't care for what he is. So I'm going to say the limit as x approaches 4 of f of x is equal to, well, how do we do this? Okay, this is what I would do for all my problems, and I think it will help you. In this problem, it's very simple, but when we get to more complicated problems, this will probably help you. You go to 4 on the x-axis and you draw a line. Okay, that's not 4, but we're going to get rid of that. This is 4. I'm going to draw this line down my page, and I'm going to call this guy here, let's call him left side, right side, okay? The left side of the page, the right side of the page. What you want to do, guys, is you want to trace the function. Follow it all the way and see where what y value it's approaching when it gets close to the x value that you want. So in this case, 4. Well, if I follow this function, when I get to 4, I'm approaching the number 0. When I come from the right side, I am actually approaching the same number, 0. So if my limit from the left side matches my limit from the right side, that means that the limit at that number is equal to that value. So in this case, 0. Okay, I hope that was simple. You just have to follow. The limit means what happens as I get really, really close to the number. So for example, let's do another one using this graph. The limit as x approaches 0 of this function, okay? So what I'm going to do here now is I'm going to get another highlighter. I'm going to go to 0, which is this guy here. This is my x0. And I'm going to say to myself, hey, what happens as I approach 0 from the left side? Well, I get to this number here, 1, 2, 3, 4, negative 4. What happens when I approach 0 from the right side? So I'm going to follow this long graph, and when I get to 0, I approach the same number. So my answer would be negative 4. And that's how we do limits. So let's try a few more examples, okay? I have a function 2x plus 1. My y-intercept is 1, and then I ended up going up 2 over 1 for my slope. So my y-intercept is 1 and my slope is 2. This is what the picture looks like. How do I find it graphically? Okay, so let's first start this problem here. Number 1. The limit as x approaches 0 of f of x as x approaches 0, right? The limit as x approaches 0 of f of x. So all I have to do is come down here. This is my x equals 0. You see I'm highlighting it. When I come from the left side, all I have to do, so let me actually just stay consistent so I don't mess anyone up. This is this guy here. I'm going to label him left. I'm going to label him right. When I come from the left side, I'm going to this number 1. When I come from the right side, okay, I'm going to the same number 1. And so therefore, it's 1, okay? So I'm going to just get rid of this highlighted stuff. Okay, so this is going to be 1. And now you might say, well, can we find it algebraically? Sure. Now, I know a lot of mathematicians will really be angry at me, but basically all you have to do is take 0 and plug them into the x. 2 times 0 is 0, plus 1 is 1. And you see how it matches algebraically? All you have to do is plug it in. Now, the reason why we don't like to plug it in is because you're not really plugging in 0. What you're doing is you're plugging in a number really close to 0. This is so important and you shouldn't miss this. When they ask you what the limit is as x approaches 0, you don't really want to put in 0. You want to put something like 0.00001, which is really, really close here. And then you want to put something really, really close here, negative 0.00001. And then that should give you 1. It's what happens when it approaches it. Let's try another one. The limit as x approaches 2, this number 2 here, the limit as x approaches 2 of f of x. Well, let's try it first algebraically. So let me get rid of this here. What would I get if I tried this algebraically? Okay, well, if I went to 2, algebraically, if I went and I plugged in 2 here, I would get 2 times 2 is 4. 4 plus 1 is 5. Now, earlier I said the greatest thing about this is that if we know the function is continuous, then we don't even have to worry about the limit not existing. The limit will always exist if the function is continuous. Let's look at it graphically. All we have to do is go to x equals 2, which is this guy here, come up, and let's see where he's going. Where is that y value at 2? The y value at 2 is exactly what we found. That guy there, that's 5. Okay, let's try one more. X approaches negative 2. X approaches negative 2. Let's try it algebraically. 2 times negative 2 is negative 4. Negative 4 plus 1 is negative 3. Now, if I come here on my graph and I go to x equals negative 2, that's this guy right here, where would I be approaching? Well, that's that guy. So 1, 2, 3, negative 3. Okay, so that makes sense there. So that's how we do that. Let's try another one. I graphed this function here, y equals x squared minus 3x plus 2. I used the two roots to graph it. I did x minus 2, x minus 1. That gives me these two roots. And I knew the y-intercept was 2, right guys? Okay, that's great. I graphed it. This is what the picture looks like. Well, so let's try first algebraically. Problem down here, number 1, the limit as x approaches 0 of f of x. Well, when you plug 0 in here, what do we get when we plug 0 in here? 0 squared minus 3 times 0 plus 2, that just gives you 2. Well, go and check it on your graph. Go to x equals 0, which is right here. What's the y value? 2, okay? Now, what about limit as x approaches, let's try this guy right here, number 2. The limit as x approaches negative 1 of f of x. Go to negative 1, and what's my answer? Okay, some number here. It looks like it's going to be 6. Let's confirm it algebraically. Well, negative 1 squared is 1. Negative 3 times negative 1 is positive 3 plus 2. 1 and 3 is 4 plus 2 makes 6. Okay? So all you have to do is go to x equals negative 1 and see what that y value is. See how easy that is? Let's try x equals 1. I'm sorry, x approaches 1. The limit of f of x as x approaches 1, that's this guy here. Oh, that's just, here's x equals 1. What's my y value when x equals 1? 0. Yeah. Isn't it true that if I plug 0 in here, which was one of the roots, that it would be, I'm sorry, that I plug 1 in, which is one of the roots, I would get 0. So that's how we do it both graphically and algebraically. You're basically just substituting it, but I just need you guys to remember that it's not what happens at 1. It's not what happens at negative 1 or at 0. It's what happens when it gets really, really, really close to it. Okay, this is a semicircle. what is the limit as x approaches 0 of f of x? You see how I'm writing it? Because you're going to need to write it like that. Well, if you go to x equals 0, which is this guy right here, what's my y value? Oh, him. That's 2. Can we show it algebraically? Sure. Let's put the 0 in here. 4 minus 0 squared is 4. Square root of 4 is 2. Great. What is the limit as x approaches 2 of f of x? Well, let's go here. That's x equals 2. Now, you see how this part here, I don't have, the domain here is only between -2 and +2. So when you take a look at and remind yourself of what I did here, this guy here is left, this guy here is right. The limit as x approaches 2 from the left side looks like it's going to 0. Is that correct? So look what I did with my notation. I said 2 from the left is 0. I had to show you the left side. That's the notation for the left side, this little negative here. Now, my big problem here is 2 from the right. Well, the limit as x approaches 2 from the right of f of x, that actually does not exist. Why? Because remember that limits is not exactly at 2, but in this case, you're basically plugging in 2.00001. If you try to do this algebraically into here, you're going to get 4 minus 4.0001 square rooted. That's going to be negative 0.001 square rooted, and we know that's not a real number. So I have to emphasize that it's going to be limit as x approaches 2 from the left side. Okay, we're going to talk about this more in our next video, but this is how we show limit from x2 to the left. This is from the right side. Notice the right side, I don't even have a graph. Okay, this is the function e to the x. Do you guys remember what e to the x looks like? It's this here. It's this guy here. Well, the limit as x approaches negative infinity, well, this is -1, -2, -3, -4, -5, -1,000, -10,000, -20,000. Where is this graph going when it goes all the way out there? You're right, it goes to 0. Some of you might say, well, can we show this algebraically? Not really, but maybe. Let's see what we could do here. E to the negative infinity, even though we shouldn't be plugging this in, I know. Negative exponent means 1 over, right? Negative means put me under 1. E is a number that's 2.718. 2.718 to a really large number. It's really, really, really large. 1 over a large number is basically 0. And now here, the limit as x approaches positive infinity, well, here's 1, 2, 3, 5, 10, 1,000, 10,000. Where's this graph going? It's going to infinity. Okay, so that's how we do this video, this problem as limit as x approaches infinity. I think you guys should stay on this video and do the rest of the problems with me. So that's how we do this. Okay, so if you want to try it algebraically, you would just put infinity. E to a large number is just really, really large. Once again, we know infinity is not even a number, but you're putting in a huge, huge number. What happens when I go all the way out here? Where's this graph going? It's going up in the air, okay? So your y value is infinity. So it goes all the way up in the air. Let's try the natural log of x. What is the limit as x approaches, I'm going to say 0 from the right side? Look, notice what I did here. 0 from the right side of f of x. Well, we know that the natural log of x has a vertical asymptote, which I highlighted in green. This guy is 0. 0 from the right, remember, we separated our graph into left and right. 0 from the right, where is this guy going? 0 from the right, all the way to negative infinity. Okay? Now, what is the limit as x approaches, let's say, 1 of f of x? Well, here's 1. It's continuous from here to here, so I don't have to worry about anything. So my answer would be just 0. Well, can we show that algebraically? Sure. You shouldn't be plugging in 1, but you know what I get. Natural log of 1 is equal to 0. What is the limit as x approaches positive infinity? We go all the way out here. Guess what, guys? Sure, it's concave down. You should know that. But remember, and it's growing very slowly, but it's still growing. So the limit as x approaches infinity is going to be large, okay? So here's just some quick examples to find the limit. We're just going to do it algebraically. All you have to do is first see if it's continuous. If it's continuous, you don't have to worry about the left and the right. In all these problems here, I made it sort of continuous-ish. So let's see how we're going to do this, okay? This is just, the first one is just a parabola. Parabolas are continuous. The limit as x approaches 0, let's just plug in 0, okay? 4 times 0 squared minus 2 times 0, that's all. 0 plus 3 is 3. Once again, you can pause the video if you would like and try the problems, okay? Negative 2 squared is 4. We're on the next problem here. Now, I know that the square roots, their domains are restricted, so you just got to be very careful. Let's put in negative 2. Negative 2 squared is 4. 4 minus 6 times negative 2, so that's going to be 4 plus 12 plus 3. That's the square root of 19. Great. That's your answer. Let's plug in negative 1. 9 times negative 1 is negative 9, plus 1 is negative 8. That's just going to be 64. Let's plug in 7. That's going to be 49. That's what the limit is. You guys can pause the video and try them yourself. Now, these two are parabolas, and we're just going to plug in. I have a few more, okay? 2 more, actually. Let's try this. What is the limit as x approaches 2 of this function here? Well, that's e to the 4 minus 4, which is e to the 0. That's just 1. This is not appropriate to do by substitution because, remember, we're not really plugging in 2. We're plugging in 2.0001 and 1.99999. You're plugging in a number to the left of it and to the right of it, and you're going to see if it approaches the same number. Here's our final one. The limit as x approaches 3, you put the 3 in here. That's 9. We know when natural log touches e, it gets rid of it, and it just leaves you with the exponent. So that's just 9, okay? So that's how we do the first part of limits. I just wanted to really kind of throw us into the pool, and hopefully in the next video, I'll teach you guys how to swim. And if you watch all the videos, everything will click at the very end. I'm trying not to make these videos really long, but I have to at some point make it long for you guys to understand. But hopefully future videos will be shorter, so come back for the next video.